Hello YouTube. In this series I'd like to look at scientific realism, which is a view in the philosophy of science concerned with the nature of scientific knowledge. So let's consider a standard scientific claim. For instance, the bacterium Yersinia pestis contains a plasmid that creates a gene that codes for a protease, an enzyme that digests other proteins. This protease allows it to destroy patrolling phagocytes of the host's immune system. That's the kind of sentence you might expect to find in an article reporting the results of a scientific study of Yersinia pestis. Now, notice that these sentences make reference to a large number of entities that we can't directly interact with. Bacteria, plasmids, genes, protease, phagocytes. The debate about scientific realism is the debate about the ontological status of these unobservable entities. So, to be clear, we can distinguish two types of entities. There are observables. These are the standard, everyday entities that can be perceived with the unaided senses. Cars, trees, water, animals, stars, mountains. Then there are unobservables, entities that can only be detected using instruments, such as bacteria, plasmids, mitochondria, electrons, protons, black holes, gamma rays, magnetism, the strong nuclear force. A significant chunk of the natural sciences is conducted in the realm of the unobservable. Now, generally, people don't take this distinction to be metaphysically significant. We assume that unobservables, such as bacteria, exist in the same way that observables, such as trees, exist. Obviously, bacteria and trees are very different, but we assume that they're both part of the world, and that the only reason we can't interact with bacteria directly is that they're just too small for us to see. When scientists make statements about bacteria, we assume that they are accurately describing part of reality. There really is this tiny organism called Yersinia pestis. It really does contain a plasmid. The plasmid really does contain a gene that codes for a particular protein, and so on. Now, this is pretty much the view of the scientific realist. The scientific realist asserts that the world is full of all sorts of unobservable entities, that scientific theories describe these entities, and that these theories are mostly correct. I guess scientific realism is basically the common sense view of science. So it's a common sense view, but a moment's reflection should lead us to be a little bit sceptical of it. In the past, many, indeed most, scientific theories have turned out to be wrong, and many entities that were postulated by scientists and that we thought were part of the world turned out not to exist. Let's look at a few examples. First of all, diseases were thought to have been caused not by infectious organisms such as the bacteria Yersinia pestis, but by poisonous air, known as miasma, which emanated from rotting organic matter. If these particles of rotting organic matter got into your body, they could cause diseases. So this is the miasma theory of disease. Second, it was believed that heat is a compressible fluid called caloric that passes from one body to another. Bodies absorb caloric, and bodies with high caloric pressure are hot, while bodies with low caloric pressure are cold. So when you put your hand on a hot stove, what's going on there is that the stove has higher caloric pressure than your hand, and so the caloric passes from the stove with high caloric pressure into your hand, which has low caloric pressure, and it will continue to do so until the caloric pressure equalizes, or until you take your hand off the stove. Different bodies have different capacities for absorbing caloric. Water is a very good absorber of caloric, whereas metal, only a little bit of caloric will make it very hot. So, this was a widely accepted theory of heat. Turned out to be wrong. A third, combustion, was thought to involve the loss of a substance called phlogiston, which would be passed to the air. When you light something on fire, the burning releases this substance, phlogiston, into the air. Now, in fact, we now know that during burning, oxygen is taken from the air and added to the burning material. Finally, consider light. By the 19th century, it was widely accepted that light was a wave. Just as you have sound waves, you similarly have light waves. Now, waves require a medium through which to propagate. Sound, as we know, propagates through the gas molecules in the air. At least, assuming you're in the air, obviously it can propagate through water, but as I'm speaking right now, the sound is propagating through gas molecules in the air. If you create a vacuum and so remove all the molecules, and you set off an alarm clock in the vacuum, you won't be able to hear it. But you can still see it. So evidently light waves don't propagate through air. We've removed all the air, and the light is still coming through the vacuum. And this led to the postulation of the luminiferous ether, which is an extremely subtle substance that permeates all of space and is the medium by which light waves propagate. It's a nice idea, but of course there is no ether. So many entities that we used to believe in, and for apparently good reasons, turned out not to exist. By induction, shouldn't we expect that many of the entities we currently believe in will also turn out not to exist? How can we know that electrons and black holes won't go the way of phlogiston and the ether? This kind of consideration has motivated a variety of more sceptical positions about unobservables. Now, before turning to these views, I think it may be worth stating scientific realism more precisely. Different philosophers will define scientific realism in different ways, but it's possible to find a basic common core of beliefs. Anjan Chakravarti, in his book A Metaphysics for Scientific Realism, outlines three core elements of scientific realism. First, ontology. There is a mind-independent world. It's a pretty simple idea. Second, semantics. Scientific theories about the world should be taken literally, and they can be either true or false. To put it colloquially, scientific realism takes scientific claims at face value. When scientists talk about electrons and so on, they are literally talking about electrons, these incredibly tiny fundamental particles that can have they have a negative charge and so on. The claims about electrons should be taken at face value, taken literally. So we might put the semantic claim in terms of the aims of science. What science aims to do is reveal the nature of the mind-independent world. Third, the epistemological claim. This claims that most of these theories are true, and they give us knowledge of the world. The unobservable entities that are postulated by scientific theories are part of the furniture of the world. Now, we do need to make a couple of qualifications to these claims. First, we shouldn't be realists about everything in science. Scientific realists generally restrict their views to mature theories. What exactly is a mature theory? Well, this is somewhat up for debate, but a few things can be said. We're generally looking at those theories that have been around for a long time and that have attained a consensus in the relevant field. Consensus is obviously important. If a theory is still the subject of much debate, then we should be cautious about believing it. Furthermore, the theory needs to have survived rigorous testing, and especially testing of novel predictions. A novel prediction is a prediction that is risky and surprising. It's a prediction of an unexpected phenomenon. For instance, Einstein's theory of general relativity predicts that a large mass will bend light about twice as much as would be predicted by Newtonian theory. This was tested and confirmed by Arthur Eddington, who took a photo of the sun during an eclipse and showed that the apparent positions of the stars near the sun matched the prediction of general relativity. Another surprising prediction was the gravitational redshifting of light. If you observe light from a large mass, the light should be redshifted. This is because space-time is literally compressed by a mass. So space-time stretches out as you move away, and the light stretches with it, shifting towards longer, redder wavelengths. This was confirmed by the Pound-Rebka experiment in 1959. Another prediction was gravitational time dilation. Time should move more slowly nearer to a large mass. This is confirmed every day by GPS satellites, which have to be frequently adjusted because time in the orbit around the Earth runs more slowly than time on the surface. Light deflection, gravitational redshifting of light, and gravitational time dilation are all surprising predictions, or novel predictions. These are phenomena that we would have absolutely no reason to expect if not for the theory. So we're looking for theories that exhibit wide consensus, a history of rigorous testing, and especially a history of confirmed novel predictions. These are mature theories. Now, many modern theories are therefore not part of scientific realism. Maybe one example is string theory. I'm not a physicist, but my understanding is that there's still a great deal of controversy about how string theory is to be understood and exactly what the evidence for string theory is. So a realist would be cautious about that. Similarly, dark energy. Dark energy is postulated to explain the accelerated expansion of the universe, but there's so much that we don't know about dark energy. We really have no idea even what dark energy is. So again, the realist would be very cautious about that. It's very plausible that the concept of dark energy will be shown to be faulty, and some completely new theory of the universe will displace it. So realists are only going to accept that mature theories tell us about the nature of the world. Second, scientific realists don't claim that mature scientific theories are completely true and completely unassailable. Obviously, we can expect that science will change in the future as we discover more things. What scientific realists say instead is that mature scientific theories are approximately true, or at least they're approximately true within a particular domain. So when physicists talk about photons, most of what they say is correct, not necessarily all. There might be a lot that we're wrong about, a lot of things we don't know, but generally most of what we say when we talk about photons is correct. As a specific example, consider Newtonian mechanics. Newtonian mechanics works almost perfectly given everyday sizes, like everyday masses, everyday velocities. It's very good even at the scale of the solar system, with predicting the motions of the planets. But if we look at very high mass objects or very high speeds, Newtonian mechanics breaks down, and that's where relativity theory enters. Of course, relativity theory isn't perfect either, but we can say that Newtonian mechanics is approximately true within the domain of everyday objects, and relativity theory is approximately true with everyday objects and at grander scales. Furthermore, scientific realists will generally assert some notion of progress towards greater truth. Mature scientific theories are approximately true, and we can expect that they will become more true over time. Relativity theory was truer than Newtonian mechanics, which itself was truer than Aristotelian mechanics, for instance. So that's the picture of scientific realism. Now, I think that you can understand scientific realism better by considering the theories that are opposed to it. There are a variety of alternatives. So first of all, let's recall the three basic claims. Scientific realism asserts belief in a mind-independent reality. It asserts that scientific theories are to be taken literally, and it asserts that most such theories are true, so that such theories give us knowledge of the world. Now, this isn't an exhaustive list, but here are some of the theories opposed to scientific realism. This table is based on a table given by Chakravarti in the aforementioned book. So, philosophical skepticism is the kind of view promoted by someone like Sextus Empiricus, also found in the hyperbolic doubt of Descartes. The philosophical skeptic is agnostic about the notion of a mind-independent reality. Maybe there is a world beyond the mind, but if so, we can never know about it. Theories are construed literally, but they don't give us knowledge. All we ultimately have access to are our own sense impressions. We can never get beyond these sense impressions to have knowledge of the world outside. Perhaps scientific work is useful for other reasons, but it doesn't furnish us with justified true beliefs about anything. And notice that the philosophical skeptic is agnostic not just about unobservables, but also about observables. We can't know even that trees and cars exist. So philosophical skepticism is a fairly extreme position. Traditional instrumentalism, or crude instrumentalism, is realist about observables. There is a mind-independent world containing objects like trees, cars, rocks and stars and so on. And when we talk about observables, our language is literal. Many of our claims are true. To say, for instance, John's car crashed into the tree, that's totally literal, and it's true if that did indeed happen. However, claims about unobservables are not interpreted literally. Instead, they're interpreted as being meaningless. Unobservables are merely tools for predicting the behaviour of observable phenomena. An observable phenomenon is something like the white streaks you get in cloud chambers. So when we talk about charged alpha particles and ionisation and so on, that helps us to predict how the cloud chamber will behave, and it allows us to systematise our observations of the cloud chamber, but that's all. So according to crude instrumentalism, claims about unobservables have no truth value at all. They don't express genuine propositions. A statement like, there is a charged particle in the cloud chamber, is no more true or false than the cloud chamber itself. Statements about charged particles, like objects such as cloud chambers, are mere tools, nothing more. But of course, by way of such tools, science does furnish us with a great deal of knowledge about the behaviour of observable things. A very popular view in the first half of the 20th century was logical positivism. I have a video called What is Meaning? Verificationism, which I recommend you go and watch if you want to know more about logical positivism, and you should know about logical positivism if you're interested in philosophy, so go and watch that video if you're not so familiar with it. But according to the positivists, all statements about both observables and unobservables are translated into statements about immediate sense impressions. So to say a charged particle has ionized fluid in the cloud chamber, that sort of can be translated to mean something like, there is a white streak in the cloud chamber. And then that, there is a white streak in the cloud chamber, is itself translated so as to refer to immediate sensory data rather than to a cloud chamber. So we'd end up with something like, there is a white streak in a black box shape that appears transparent. Or translucent, or something like that. All scientific claims are interpreted non-literally as ultimately being translatable to descriptions of immediate sense impressions. And interpreted this way, science gives us a great deal of knowledge. Now, the positivists were kind of agnostic about the notion of a mind-independent reality. We have access to our own sense impressions or our own sense data, and that's all. And the positivists regarded the question of whether there is an external world behind this sense data as a kind of pseudo problem. It's meaningless, basically, because there can be no evidence one way or the other. There's no way of testing for an external world. There's no experiment you could do to show that it either exists or doesn't exist. And they felt that any question that you can't answer by experiment is just a meaningless question. It's a pseudo question. So the question of a mind-independent reality is meaningless. So positivism it does not assert a mind-independent reality. It finds that question meaningless. Theories are construed non-literally, but theories do give us a lot of knowledge, having been construed non-literally. Constructive empiricism is a more recent view. It's defended most famously by Bas van Frassen. Constructive empiricism accepts that there is a mind-independent world, and it accepts that scientific theories should be construed literally. Claims about unobservables are quite simply claims about unobservables, and they can't be, they're not to be translated into claims about observable phenomena or anything like that. However, science does not provide us with knowledge of unobservables. The constructive empiricist claims that the point of science is empirical adequacy, and a theory is empirically adequate just in case what it claims and implies about observable phenomena is true. Okay, that's all. Empirical adequacy simply requires that the theory is correct about observable phenomena. And accepting a theory, according to a constructive empiricist, need involve nothing more than believing it to be empirically adequate. We can never be anything more than agnostic about the nature of the world beyond the observable. So the constructive empiricist rejects the epistemological claim with respect to unobservables. Science, that there's a mind-independent world, scientific theories are to be construed literally. Scientific theories give us knowledge of observables, but with the unobservables like electrons and protons and so on, we should be agnostic. Now, in modern debates, the ontological and the semantic claims tend to be taken for granted. Most philosophers assume that there is a mind-independent world and that scientific theories should be taken literally. So the primary challenger to scientific realism these days is constructive empiricism. And I do think that constructive empiricism is the more prima facie plausible of these anti-realist options. It does seem that there is a mind-independent world, and it seems like when we talk about electrons, we're just talking about electrons. Simple as that. So constructive empiricism is a nice, simple theory. It's in large agreement with the scientific realist, but the constructive empiricist just claims that we don't have knowledge of unobservables. Now, obviously, this isn't an exhaustive list. There are many different anti-realist positions, but this should give you some idea of the state of the debate. Now, it's worth noting here that alternatives to scientific realism are in no sense anti-science, right? All parties to this debate agree that science is extremely useful and important, and we should continue pursuing it. Indeed, the logical positivists, despite denying scientific realism, were aggressively pro-science. Philosophy has probably never seen a movement as militantly scientific as logical positivism. So to be an anti-realist doesn't mean that you're in any sense against science. What we're interested in is the nature of scientific knowledge. Does science actually give us knowledge of the observable world, or is it doing something else? Anyway, hopefully this has made clear exactly what the three realist claims are saying. Obviously, realism answers yes to all of these questions. So to put my cards on the table, I'd say that I'm pretty much a scientific realist, at least about most domains of science. And I think there's also a great deal of social construction involved in science, but my inclination has always been broadly realist. So that's where I'm coming from in doing these videos. Now, there are important variations on the basic realist position. Realism can be restricted in various ways. Two of the most popular variations on standard realism are entity realism and structural realism. We'll examine both of these theories in much more detail in later videos, but I'd like to outline them both here. Entity realism claims that we should believe in the existence of many of the entities described by scientific theories, but that we should be more agnostic about the theories themselves. For instance, we should believe that electrons exist, but be sceptical about what current physical theory tells us about electrons. By analogy, we believe that humans exist, but we might be very sceptical about sociological theories of human behaviour. Entity realism is most famously supported by Ian Hacking, and it arose out of a concern with scientific practice. Hacking suggests that a crucial feature of unobservable entities is that we can interact with them. Experimental scientists play around with unobservables and manipulate them and use them as tools to study other phenomena. For instance, we can shoot polarised electrons against a supercooled ball of niobium, and this induces fractional charges that allows us to look for quarks. We have built photon guns that allow us to spray streams of photons. Hacking has a lovely quote that sums up his view: "If you can spray them, then they're real." We must believe in the entities postulated by scientific theories because we manipulate those entities in scientific practice. If we're literally using an entity as a tool, we really have no choice but to believe in it. From the point of view of an experimental scientist who's firing electrons and spraying photons and so on, and using these to build knowledge in practical experiments, it's really just fatuous to say that electrons and photons don't really exist. And of course they exist. I'm spraying them. Of course, this does not license wholesale belief in all entities postulated by science. It's only those that we can manipulate. Many astronomical entities, such as gravitational lens systems, neutron stars and black holes, are not open to manipulation. So the entity realist may be sceptical of these. Ian Hacking has a paper called Extragalactic Reality, in which he argues for agnosticism about many astronomical entities. Structural realism is essentially the opposite of entity realism. Structural realism promotes skepticism of entities like electrons, but it holds that we should be realist about the theoretical or mathematical structure. So, what do we mean by structure? Well, this is a source of much debate, but an example should give an intuitive idea of structural realism. Here's a diagram showing the behaviour of light. So this shows what happens when light travels from one medium to another. So this is the first medium, and this is the second medium at the top. We have the incident beam in the first medium. So this is the light coming towards the second medium. Then this shows the light that is reflected off the medium, and then this shows the light that is that travels through the second medium. As you can see, it gets refracted or bent as it travels through the second medium. Now we can say various things about this situation. There's a very simple law for reflection. The angle of incidence equals the angle of reflection, at least assuming that the surface is smooth. Whatever angle the light comes in at is equal to the angle it's reflected. The angle of refraction depends on the medium through which the light travels. It's a bit more complicated, but it's given by something called Snell's law, which says that the refractive index, labelled N1, of the first medium times the sine of the angle of incidence, or I, there, is equal to the refractive index N2 of the second medium times the sine of the angle of refraction, or R. An equivalent expression is in terms of velocity. The light has a certain velocity, v1, through the first medium, and a slower velocity, v2, through the second. v1 over the sine of the angle of incidence is equal to v2 over the sine of the angle of refraction. You can look up Snell's law if you want more of an explanation, but the point here is just we have some mathematical equations which describe the behaviour of light. Now, all of this was well known when ether theory was accepted. What's interesting for our purposes is that when ether theory was displaced, and it became known that light is composed of photons, these strange entities that have both wave and particle properties, these laws were retained. Our understanding of the behaviour of light on a mathematical level survived the elimination of ether theory. The behaviour of photons obeys laws that are pretty much identical on a formal level to laws describing the action of waves in the medium of the ether. So this is the kind of thing we mean by structure. It's the mathematical relationships. And the structural realist says that over the history of science, the entities are eliminated, but the structure is preserved. So we should be realists about structure. Again, we'll talk more about entity realism and structural realism later. One final thing that I think is worth noting is that different views may be appropriate for different domains. You could, in principle, be an entity realist about biology, a structural realist about chemistry, and an anti-realist about astrophysics, for instance. Most philosophers seem to look for a universal theory that applies across the board, but this isn't required. The standard assumption, it seems to be that science is essentially a unified enterprise, that the sciences are all they all apply pretty much the same methods to different parts of the world. So, one philosophy of science would be appropriate for all of them. But of course, this is very questionable. If the sciences are fundamentally disunified, fundamentally just messy and separate, then we shouldn't expect one theory to fit all the sciences. So, so that's scientific realism. A kind of brief introduction. In the next videos, we'll look at the arguments concerning scientific realism, and we'll again look in more detail at some of the variations on the basic view. But that's the basic picture, the basic scientific realist picture. So I hope that was useful. That's all I'm going to talk about today. Thanks for watching.